Good day, everyone. This is our water resources presentation, and our group members are as follows: Akili Phillips, myself, Ian Dixon, Gavin Rogers, Nathan Treasure, Ravina McLeod, Kennedy Matheson, and Romain Arjun. For this presentation, our objectives were to discuss the background and of the area, the site findings, the potential solutions, hydrology, inlet and channel type, canal route and inlet location, the hydraulic design, and the economic comparison.
Okay, so for this project, the street that we will be assessing is the Marcus Garvey Drive Road. In March 2016, contractors and the government of Jamaica decided that they would renovate the Marcus Garvey Drive Road. They spent approximately $20.5 million to execute the improvements. However, in 2020, the island experienced severe rainfall due to the hurricane season, and that caused um, sorry, major flooding on the road. In January 1970, Marcus Garvey Drive Road was formerly known as Shore Road. It was created due to the construction of the Portmore Causeway, and the contractors and engineers decided that the road had to be extended and couldn't just start and end where it was. Also, the business inhabitants of the area decided it would have been a good idea. One of these business places were Petrojam, formerly known as Kingston Refinery. Jamaica has one of the highest water tables in the Caribbean. Therefore, when the road was being built, it was underdumped and it was dumped with granular and foam. Now, due to this, the drainage system was directed right back into the soil, which is already waterlogged, as well as it was oversaturated, and that is one of the main reasons for flooding.
Okay, so site findings. So to gain a better understanding of the situation at hand, the group members decided to conduct a site visit to understand the extent and to better be able to develop solutions for the problem. So upon investigation, numerous problems were seen with the drainage system that exists. Problems seen included insufficient drain size, inlet clogging, polluted and blocked drains, and inadequate outlet streams. So we are going to look at some of the images that were taken upon our site investigation. So starting with the photo on our left, we can see that there's an inlet that is clogged with pebbles and stones, and therefore will cause a backup of stormwater and drainage. On the right is also an inlet, but as we can see, it is covered with dirt and has vegetation which is being grown in it, and therefore highlights the fact that maintenance would be needed for these inlets. So with the photo on the left, we can see that we have an outlet which has a lot of vegetation, which indicates a lack of maintenance, which will furthermore hinder the flow of stormwater. On the right hand side, we can see that we have another outlet which is quite narrow, and therefore it can be seen that it can't handle the volume of water, and therefore it will be easily overflown. So with the photo in the top left, is also an outlet which water flows from on Marcus Garvey Drive, and as you can see, there's a lot of vegetation growing on the sides of the canal, which holds the water in place and prevents the flow of water, and furthermore makes the stormwater backs up. The photo in the lower right, we can see it's a photo showing a lot of pollution, which also adds to the backing up of stormwater, and therefore it needs to be maintained and cleaned up. So the photo on the left, we can see where the outlet meets the drainage, and once again there's vegetation which will prevent stormwater flow. And on the photo on the right, we can see is a canal with a fridge inside, which indicates how heavily polluted it is, as shown once again that it is preventing water from flowing. Now with the photo here, the problem we have is that the size of it cannot accommodate the amount of volume of water that is flowing through it, as the depth is approximately 2 feet, which is simply not enough, and therefore a solution is needed for this part of the drainage system. Now here is a picture of the side of Marcus Garvey Drive, and what is highlighted here is the side of the road, as when there is heavy rainfall, the road is flooded and stormwater has nowhere to flow, and therefore overflows on the sidewalk and into the parking lots, which causes the backing up of stormwater and flooding. So here we can also see that there is heavy pollution along with a lot of vegetation, and it is evident that there is little to no maintenance here, hence the state that it is currently in, and therefore a solution will be needed for this as well. So for the image on the left, it shows a small path for the stormwater to take. This cannot handle large volumes of rainfall, and therefore it can be easily overflown, which will go onto the roads and sidewalk. So therefore, what was deduced was that it is not meeting the required amount of stormwater intake it was designed for. And on the right, it is simply showing the close-up of one of the inlets on the sidewalk, indicating where stormwater is supposed to flow. Now here's a strip of vegetation where a lot of frequent flooding occurs, as a lot of water is held here when there is heavy rainfall. Therefore, there needs to be a solution for it, as it adds to the severe flooding on Marcus Garvey Drive.
All right, so solutions to the problems at hand are we can improve the maintenance of the drains and the inlets. Secondly, we can install inlets at the bus stop. We can also widen the existing drains. We can also install an underground pipe to connect from the side with no drainage to the side with the existing drainage. And finally, we can create an open drain at the grass area to collect stormwater.
Okay. An alternative solution would be a flood tunnel. Now, the idea of a flood tunnel came from Tokyo in Japan. Now, the city of Tokyo is being held up by tons of columns underneath the city. Now, the idea to solve the Marcus Garvey problem is to rebuild the road just like the Tokyo flood tunnel. Now, to do so, we would have to take a piece from the Tintipen airdrome and rise the road. But in reality, that is impossible because of the guidelines for airways, where the roads cannot be too high so that they can have a safe landing. Also, the budget for this project at the time was 2 billion US dollars. It is very cost effective, and the cost analysis works out because in the long run the country and the inhabitants of the road would benefit.
Okay, so when it refers or when we speak about hydrology, we're referring to the surrounding area of our area of focus. Now, our area of focus is the Marcus Garvey Drive, the driveway. So we're only focusing on a small section of it, and as you can see right here, to the left of the area of focus, we have Kingston Wharves, which consists of a paved surface. To the right, we have grasslands, which is the airfields. Also, when we're talking about hydrology, we're mainly referring to the catchment area. Now, the catchment area is the amount of area that has water which contributes to our area of focus. Now, let's say, for example, Kingston Wharf is contributing a specific amount of water, and the airfield is contributing a next amount of water to our area of focus. Now, this area that is contributing water from each of those sites would be considered into our catchment area. But based upon analysis, we realize that the only area that is giving or providing water to our area of focus is the part of the Portmore Highway. So along with this part of Portmore Highway and the area of focus itself sums up to give us our catchment area. Now, based on this map, you can't exactly see the values that are stated, but beside each black dot, there is a specific rain value. So this is a rainfall map for a 10-year return period. Now, for our area of focus, where we determined or saw that the rainfall value would be 180.6 millimeters. Now, we need this value to calculate our rainfall intensity. Now, using this ratio and constant formula or table, we'll be able to get the specific ratio needed for calculations. So we're using a 10-year return period and a duration of 10 minutes. So our ratio would be 0.4. Now using this 0.4 value along with the rainfall value, which was 180.6 millimeters, we will then determine our rainfall intensity later on in the hydraulic design section.
So in the selection of an inlet, many factors have to be considered. Factors such as maintenance, efficiency, and the inlet's capacity are integral in this process. The capacity is dependent on roughness, the gutter longitudinal slope, the total gutter flow, and the inlet configuration. So we see that the efficiency of an inlet is the percent of total flow that the inlet will intercept under a given set of conditions, according to Johnson and Chang in 1984. The inlet efficiency is dependent on the cross slope, the longitudinal slope, the interception capacity, the total gutter flow, and the pavement slope. So therefore, after careful and extensive analysis, the inlet that was selected was the curb opening inlet. So according to the Stormwater Studio, a curb opening inlet is a vertical opening in the curb covered by a top slab. So these inlets are effective at locations where the flow at the curb is sufficient for the inlet to perform efficiently. We see that the curb opening inlets, they are relatively free of clogging and offer little interference to traffic. So right here we have a cross section of the curb opening inlet to your left. We see the curb opening, depression, and the collection chamber. And to the right is another visual representation of the curb opening inlet. Now, as engineers, we're the ones who assume the specifications of our project according to our assessments. And the specifications that we assumed the curb opening to be 7 feet. KT, which is a constant, is 0.6. The gutter flow we have as 2.97 CFS, which is cubic feet per second. The gutter slope we have as 0.015 feet per feet. Manning's value we have as 0.016. The cross slope of the pavement we have as 0.035 feet per feet. The depression we have as 0.75 feet per feet. And the ratio of flow we have as 0.084. Now, to calculate LT, we need to first calculate SC. So we calculated SE to be 0.098. And now, in calculating LT, we're going to sub SC into LT. So in subbing SC into LT, we got LT to be 12.95 feet. Now, if the specified inlet length is larger than LT, it will capture 100% of the flow, and Q captured will be equal to Q. And if the specified inlet length is less than the captured LT, the computed LT, then Q captured is allowed to be computed as follows. So since the 12.95 feet is greater than the 7 feet that we have to calculate the efficiency for our inlet. And the efficiency we got for our inlet is 75.3%. Now to calculate Q captured, we have it as QT times the efficiency. So it's a 2.97 cubic feet per second times the efficiency of 75.3%, and we have 2.236 cubic feet per second.
So for the channel type, solutions for this problem would both include open and closed channels. The open drains will be made of concrete and high-density polyethylene pipes will be used for the closed drains. This slide shows a visual representation of how the channels will be laid out. However, the sizing of the channels will be different as they will be about 2 feet.
So for the canal routes, for the patterns of the drains, it can be seen that on the way downtown, the gully is further down. Even though the gully is large enough to handle the amount of stormwater that is going to it, the distance that it travels is a very far distance, and the current canals that you have there aren't able to carry the large amount of water to the gully. So what we plan to do is to run underground run pipes underground to carry the storm water from one side of the road coming from downtown to the side where the drain currently exists, and then widen those drains so that it will be able to carry the volume of water to the gully that currently exists. So for inlets, we'll be installing a total of 8 inlets on the lane coming from downtown heading towards Portmore. 4 inlets will be installed towards the grass area near the overhead bridge, and the other 4 inlets will be installed further up the road going to the wharf side. So for the manholes are small covered openings in a paved area allowing for access beneath, especially one leading to sewer or stormwater line. Manholes allow for cleaning, inspection, and repairs. So there are 3 different types of manholes. You have the shallow manhole, normal manhole, and deep manhole. So the shallow manhole are called inspection chambers, typically from 2 to 3 feet deep. Normal manholes range from 3 to 5 feet deep, and they have a step ladder that's attached to it. And the deep manhole is anywhere from 5 feet deep, from 5 feet or deeper. And the normal manhole as well as the deep manhole are equipped with heavy duty manhole covers. So due to the fact that the inlets will not be having any gradage covering, we'll be using the manhole to clear out any debris and blocking that are present in the line. We'll be using a normal precast manhole to connect the drains, and also in areas where we'd have to change the direction of the channels. So typically manholes are spaced anywhere from 300 to 500 feet apart, and we're going to make them so that persons can walk through so that we can have the channels properly cleaned.
All right, so for the hydraulic design, using the guideline provided from NWA, we use our calculated specific values. So the first value we got, or the first thing that we calculated, was the average runoff coefficient, where A stands for the A value stands for the various areas of the subcatchment, and C stands for the runoff coefficient. Now, for average runoff coefficient, we got 0.9, which is quite common for a paved area. Next, we have the inlet time, or time of concentration. Now, using Krebs formula, we have where L is the flow length, S is the slope gradient, and N is the coefficient of roughness for Krebs formula. And then using that value, or the coefficient of 0.013, using a length of 1,000 meters, this is the length of the entire route or the drainage path, we got an inlet time of 14.03 minutes. Now, for the rainfall intensity, as said before in the hydrology segment, using the ratio of 0.4 and the rainfall value of 180.6 millimeters, we got our rainfall intensity to be 173.38 millimeters per hour. Now, our peak discharge, using the values that we calculated before, which are the runoff coefficient, the rainfall intensity, and the catchment area, we determined our peak discharge with a 10% surcharge to be 0.0000433. For hydraulic design for our rectangular channel, using the formulas stated in this image where A is equal to WD and wetness parameter is equal to W plus 2D, we got the channel area to be 6 feet squared, our wetness parameter to be 7 feet, and our hydraulic radius to be 0.8571. Now, the hydraulic radius is calculated by uh, the channel area divided by the wetness parameter. So next we'd have to determine the flow velocity. So the flow velocity, where n is the Manning's roughness coefficient, r is the hydraulic radius, and I is the channel gradient, we can determine our flow velocity. Now, given the lack of data, we had to assume a gradient. So we assumed a gradient of 0.01 for for all of our slope values. So with that, we got a velocity of 6.02 meters per second. Next, we find the gutter flow time. So using the length of the gutter divided by the velocity that we just calculated, flow velocity, we got a gutter flow time of 3 minutes and 15 seconds. Note that this is the entire length of the channel, which is, we assume, are estimated to be around 1,000 meters. Next would be our hydraulic design for a trapezoidal channel. Now, using the formulas that are stated in the image, we got our channel area to be 5 feet squared, our wetness parameter to be 9 feet, and our hydraulic radius to be 0.556 feet. Now, using back the same formulas for the flow velocity and the gutter flow time, we got our flow velocity to be 4.51 meters per second, and using a length of 150 meters, we got our gutter flow time to be 55 seconds. Next is our circular pipe, which would be the HDPE pipe, which would be our closed channel. So using the formulas that are stated in the image, we got our channel area to be 1.57 feet squared, our wetness parameter to be 3.14 feet, and our hydraulic radius to be 0.5 feet. Now, we're reusing the same flow velocity equation and gutter flow time. We got a flow velocity of 5.25 meters per second. Now we can note that for this, the Manning's roughness coefficient is changed to 0.012. That's due to the change in the channel. Now we got our gutter flow time, assuming a length of 170 meters, to be 54 seconds.
Okay, so now we'll be doing the economic comparison. So economics is a social science concerned with the production, distribution, and consumption of goods and services. It studies how individuals, businesses, governments, and nations make choices about allocation of resources. So in this case, an economic comparison will entail reasons why each particular solution was selected for resource allocation. Alright, so we'll be doing the economic comparison for 3 of our solutions: the inlet types, channel types, and the manholes. So for each of the solutions, they'll be further compared based on 3 categories: applicability, which deals with how practical it can be implemented, the cost for each solution, and the maintenance and efficiency for the solutions. Alright, so dealing with the inlets first, there are 3 types of inlets we'll be looking at: grate, curb, and combination. So for the grate inlet, basically the water falls into the inlet through a grate instead of an opening on the curb. So there'll just be the drainage below the surface of the road, and there'll be a grate above certain sections of it. So for the curb, a curb opening inlet is a vertical opening in the curb covered by a top slab. So there's basically a depression on the side of the sidewalk which allows the water to flow. So it basically directs the water into that opening. And for the combination, it's basically what it sounds like. It's a combination between the grate and the curb opening inlets, so it has the benefits of both. In terms of applicability for the grate inlet, They are the least efficient in terms of the stormwater capture capacity, and there is little runoff reduction on a grade, so they work best on flat surfaces. The part of the spread that reaches the grade diameter simply goes by without being captured by the grade. So basically there will be the grade width, and if the stormwater flow is of a greater width than that, the amount that passes the diameter just goes by without being captured. And there is just the problem of clogging is also significant for the grade inlets because debris is always getting caught in the grades. Alright, so the applicability of the curb inlet, there is high capture capability, so it captures a lot of the storm water. They work well in sags and on grades of less than about 3%. That's self-explanatory. So municipalities prefer to use recessed curb inlets with major depressions because this helps to capture a lot more of the stormwater. And the curb transitions may create a traffic hazards because some of the road users may not know how to navigate areas with curb inlets well. So the applicability of the combination inlet. So these inlet offer design for overflow, so even if a part of the inlet gets clouded with debris, there is a section of it that's designed for overflow, so the stormwater will still be able to be captured. So the capacity of the combination inlet comprises the sum of the capacity of the grate and the curb open inlet because it's a combination of both. It has the benefits of both of them. Alright, so here's a table with the advantages and disadvantages of the inlets. So for grade inlets, they perform well with a wide range of grades, but they can become clogged and lose capacity with an increasing in grade. For curb opening inlets, they do not clog easily and they are bicycle safe, but they lose capacity with an increase in grade. For combination inlets, they have a high capacity and do not clog easily, but they are more expensive than grate and curb opening inlets because they are a combination of both. Alright, so looking at the cost, so we'll look at the cost for the grate and curb opening inlets because they are the most practical solutions. As I just said, the combination inlet is too expensive. And so looking at the labor cost first, you can see that the labor cost to install a drain is about $50 to $100 per hour. It takes about 12 to 72 hours total for the installation, and you need about 2 or 3 people to work on that project, and you have to budget for time for demolition and reinstallation. Alright, so for the curb inlet, so based on research, we actually found this table which outlines the unit cost for a curb inlet, and this unit cost includes demolition, installation, materials, and so this is just a rough estimate. So if we look at the A10 curb inlet up to 8 feet deep, it costs about $3,500 per unit for the curb inlet. Alright, so for the grated inlet, based on research again, we concluded that it costs about $3,000 for demolition, installation, and materials to be used. But if you're looking at the inlet protection, which is the grate itself for a 15-inch inlet, it costs about $300. You add that to the $3,000, comes to $3,300, which is close to the cost for the curb inlet, which is $3,500. So the cost for each solution isn't that far apart. Here, so for maintenance, now looking at the curb inlet, the capture efficiency is dependent on the length of the opening, the depth of flow at the gutter flow line, the street car slope, and the longitudinal gutter slope. So if the curb opening is long, more of the stormwater flow will actually be captured by the inlet, but it's actually uneconomical to design a curb opening inlet that's long, but actually too long. So it actually depends on the flow of the stormwater because you can easily over design, and that would just cost more and not match up to the capacity that you want. Alright, so maintenance for the grate inlet and efficiency. It's an ideal access to the stormwater drain system because the grate itself can be easily removed and gives access to the drainage system. But the maintenance for these grate inlets is high because it actually collects a lot of debris, dirt, stone, etc. And passage of the surface water through the inlet is obstructed because of these blockages with debris. Alright, so the efficiency of the combination inlet. So this actually has the removal capabilities of the curb opening inlet and also the capture efficiency of the gray inlet. So it's actually the best of both worlds, and it intercepts about 18% more than the gray inlet alone, and is much likely to get clogged because, as I said before, it's designed with an overflow in mind. So even if the grate itself is clogged, the stormwater can still be drained out. Alright, so looking at the economic comparison for the channel types now. So engineers and administrators often have a preference for closed drains rather than open channels because they are more accustomed to them. So looking at the left hand side, you can see an example of an open drain, and on the right hand side you can see an example of a closed drain. Alright, so for the applicability of the closed drains, they do not take up surface space. This is self-explanatory because they are laid beneath the ground, so that's a plus. They also reduce the risk of either children falling into them if they were open drains, or vehicles falling into them, or any sort of risk like that. Then they have self-cleaning flow speeds designed in mind while being designed, so if the flow speed is high enough, you wouldn't have to worry as much about the cleaning of the closed drains. Alright, so for open drains, you have to keep access bridges in mind for to join the properties and the roads together for pedestrians and vehicles that live nearby to get over the open drain itself. They are simple to construct. Construction materials are often locally available. Creates employment for construction and maintenance, but there is high health risk due to an illegal discharge of wastewater and solid waste into the open drains because people find it convenient to dispose of garbage into them, and blockages can easily spill over and cause flooding. Alright, so the cost for closed drains, they actually cost more to build because they require deep excavation, must withstand the heavy loads and street overhead, and require expensive additional work such as manholes and inlets. And they also require more sophisticated engineering techniques as well, so this just adds to the cost. And we give an example here for a section of a closed drain that costs about $46 per meter. So for open drains now, they are low-cost drain solution if a drain already exists. They are a less expensive solution generally, and the precise cost depends on the local conditions such as how steep the terrain is, and also very flat areas could raise the budget cost as well. So this is a table which outlines the cost per meter for open drains. Right, in terms of maintenance now, so for closed drains, construction defects, deterioration, and accumulation of debris could be a problem. So because they are closed, you actually need maintenance in order to clean them when they are backed up inside. There can be cracks and defects if they are prefabricated based on the technique, so that actually adds to maintenance. They require more sophisticated engineering techniques, as I said before. And because there are closed drains, mosquito breeding can be difficult to control, and if the sewage is slow moving, the gases can build up and actually affect the construction material which makes up the drain. Alright, so for open drains, the cost for maintenance would be about 8% of the construction cost according to WHO. Keeping drains free of refuse poses a problematic obstacle. As I said before, people use it to dispose of garbage or wastewater, grey water, anything like that. There are health risks because of pathogens and viruses that can actually build up in these open drains because of the waste. So the cost of manhole, the type of manhole selected is fairly straightforward. We decided on a normal manhole previously, so only the cost will be outlined. So unit cost for storm drain structure and sewer manholes are assumed to be pre-cost. So in this case, we're assuming that we'll use a 72-inch diameter manhole, which is about 6 feet, and that costs about $5,600. And so the 72-inch diameter manhole up to 8 feet deep fits with the parameters of a normal manhole and costs about $5,600. And as stated before, this is the smallest acceptable manhole that we'll use, and any larger size manhole that we use would be more expensive per unit.
Okay, so to conclude, the background information and all the objectives were answered throughout this presentation, and we got to do in-depth investigation on Marcus Garvey Drive. If you have any questions, feel free to contact us. Here's a list of our references that we use to orchestrate our presentation. Thank you.